Okay, in this lecture we're going to finish the last part of our section 11.4 material on tangent lines and the derivative. So in this last part of our section we're going to consider how we could use the graph of a function in order to obtain the graph of the derivative, and we'll see that the graph of a function or a derivative might be giving us some useful information when we get to later chapters in this course. So in this example, we are given the graph of a function f. So here the graph of some function f is given. And the problem is to sketch the graph of the derivative of this function. Now, in this example, we have a problem that's a little bit different from what we've been considering. We know if we have a formula for f of x, we could find the derivative using that limit definition of the derivative, and once we find our derivative, we could sketch the graph of it. But in this example, we don't know what the function f of x is. We're just given a graph of it, and we have to use a geometric interpretation of the derivative in order to get the graph of that derivative. So there's three parts to this example. In part A, we have the graph of a function a shown here in blue. Let me trace over it because it's a little light. So we have the following graph, and the assumption is that it continues in this direction infinitely, in both directions. So let's think about how we could try to obtain the graph of the derivative of this function. Now we know that the derivative represents the slope of the tangent line to the graph of this function at a point. So as we move along the x-axis from left to right for this figure, let's sketch little tangent line segments along the length of this curve. So when I start maybe choosing a point on my curve here, we see that the tangent line would be the line passing through that point, which has this slope. So it's sort of a large negative slope. And as I start to increase the value of x, the slope of this tangent line is still negative, but it looks like it's starting to flatten out. It's a smaller negative number until I get to this value of x. Let's maybe call this point A. And I see that at this point on my curve, my tangent line would be horizontal. That is, I have a zero slope for the tangent line. And as I keep moving from left to right along the x-axis, now I get a tangent line where my slope becomes positive. And as I increase the values of x, I'm getting positive slopes, which are starting to flatten out a little bit. They're not quite as large. Until we get to this x value, let's call this x equals b, where, again, I would have a horizontal tangent line, or a tangent line of zero slope. And as I keep increasing the value of x, now again I find the slope of my tangent line becomes negative, and the larger that I'm making x, it looks like my slope is getting steeper and steeper. So how can I use this to sketch the graph of my derivative? Well, we found in this sketch for our tangent lines that at the values of x equals a and x equals b, our tangent line was horizontal. That is, it has zero slope. So the derivative at those points, a and b, should be 0. That is, I have my graph of the derivative intersecting the x-axis, or my y value for the derivative, is 0 at x equals a and b. Now let's think about what the derivative looks like in between these points. So moving left to right, we said that initially we were starting with relatively large negative values for our slope. So I start with some relatively large negative value for y for the corresponding value of x here. And as my x values start to increase from left to right, we said our values for the derivative, that is the slope of these lines, were all negative, but they were starting to flatten out. That is, we're getting smaller and smaller negative numbers. So the graph of my derivative starts to increase. So we're getting smaller negative numbers. And we know that when x is equal to a, we have to pass through this 0 point where we had a horizontal tangent. Now, once I pass through that value x equals a and I keep moving to the right, now the slope of our tangent lines becomes positive. So the graph of our derivative starts to rise above the x-axis, so we have positive values for our derivative, up until I hit x equals 0. Looks like our slope of that tangent line might be about 1 or something. And once we move past that, the slope of our tangent line starts to flatten back out. So it's still positive valued, but now it's a smaller positive value. It's decreasing. And as we get to the point x equals b, again, we have a horizontal tangent line. So we know we're passing back through 0. And as we keep moving past that value, x equals b, the slope of our lines again becomes negative. And the larger that I take the value of x, the larger negative slope I have. So the graph of my derivative, which represents the slope of that line, starts getting larger and larger in the negative direction. So for this function, I have a derivative, y equals f prime of x, whose graph looks something like this. All right. So in part B, we have a curve, which is the graph of some function, y equals f of x. And I'm going to use the same sort of approach here that I used in part A. So I might start by looking for the points on my curve where I have a horizontal tangent line. And I see here that at this value of x, let's call this maybe a, I have a horizontal tangent. When x is 0, I have a horizontal tangent. And when x is b, looks like I have a horizontal tangent. So for the graph of my derivative, when x is a, 0, or b, I'm going to have a derivative which is 0. So those are going to be my intercepts for the graph of the derivative. Now let's think about what the derivative or the slope of my tangent line looks like outside of those values or between those values. So as I'm moving from left to right along my x-axis, the slope of the tangent line to my curve starts by being a relatively large positive value. And I see that as I start to increase the value of x, the slope of my tangent line starts to flatten out. So for the graph of my derivative, I started with relatively large positive values for the derivative, that is for my y values, and then the tangent line, or slope of my tangent line remained positive, but started flattening out, decreasing towards 0 until we hit that point x equals a, where we had a horizontal tangent. So we're passing through 0. Now between a and 0, if we choose a point, the slope of my tangent line now becomes negative. So the slope of our tangent line, which is our derivative, becomes negative. It dips below the x-axis. And then it starts to flatten back out towards 0 at x equals to 0. Now between x equals 0 and b, if I choose a point, I see that my tangent line is again positive, or has a positive slope. So between x equals 0 and b, our tangent line will become positive, and it starts to flatten back out as I approach b, so heading back towards 0. And then once I move past x equals b, I can see the slope of the tangent line to my curve becomes negative again, and the larger that x is, I have a larger slope for my tangent line, so I'm getting larger and larger negative numbers as I keep increasing the values of x. So my derivative, y prime, or y equals f prime of x, is shown here. So in my last part of this example, part C, we have the graph of a function which consists of these straight line segments. And when I think about how to get the graph of my derivative, well, let's look at the graph of this original function. So I notice when I look at the graph of this function that there are two values of x, let's maybe call these a and b, where the graph of my function has a corner. So recall, if the graph of your function has a corner at a point, it is not differentiable at that point. So at these values a and b, we have a derivative which is undefined. So let's see what that's going to look like here. Now for values of x that are to the left of a, as I'm moving from left to right towards a, well, my function is a straight line segment. So the tangent line is exactly equal to the function itself. And we see the slope of that line segment is a positive constant value. So for the graph of my derivative, I have some positive constant slope. So the graph of a constant is a horizontal line until I get to the value x equals a, where I hit a corner and my derivative is undefined. So I'm going to have a hole in the graph of my derivative. Now once we move past a, everywhere from x equals a to b, our function is a line segment. So our tangent line is exactly that line segment, and it has a constant negative slope. It looks like the same value as the positive slope that we had to the left of a. So I'm going to jump downward to have a constant negative slope everywhere from a to b. And again at b, we had a corner, so I'm going to have a derivative which is undefined at b. I'm going to have an open point in the graph of my derivative. And then once we move to values of x that are greater than b and keep increasing, we see that our function is a line segment of constant positive slope. It looks like the same slope that we had for values of x to the left of a. So I'm going to jump back to the same positive constant slope that we had for values of x to the left of a, and I'm going to have that same slope for all values of x there. So we have a derivative y equals f prime of x, which is discontinuous because of the way that our function was defined. We had corners in the graph of our function, so there are points where our derivative does not exist, namely the points a and b, and we might have jump discontinuities in the derivative of our function if it's defined in this way. So in this example, we see that if we are given, or if we're able to sketch the graph of a function by thinking about the derivative as the slope of the tangent line to the graph of that function, we can obtain at least a rough sketch for the graph of our derivative of that function.